Hello, everyone. I hope you are staying home very safely. And today, I'm going to talk about the ideal Otto cycle analysis. Okay? So please read the chapter 9.5 to understand better about what I'm going to talk about today. So at the end of this lecture, I really hope that you should be able to answer those two questions. The first question is, how can we calculate each state of the ideal Otto cycle? And second question is that how can we calculate the power output and the thermal efficiency of the ideal Otto cycle? Now, before we go further about that ideal Otto cycle analysis, let's review what we learned on the last lecture. So we learned about spark ignition engine as a part of gas power cycle. Okay, so if you look at the spark ignition engine, particularly if you look at the 4-stroke spark ignition engine, then you can see that that cycle, that engine, should have 4 strokes to make one cycle. It starts from intake stroke, where the fresh air and fuel mixture comes into your engine. Then the next stroke is compression stroke. That piston moves up to compress the fuel and air mixture to make it high pressure and as a result also high temperature. As soon as that stroke is over, then the spark plug that is a part of the engine ignites the spark to initiate the combustion process. Okay? And after the combustion process, this air and fuel mixture becomes totally burned gas, and the resultant pressure and temperature is drastically high. And that is so intense to push the piston back to the bottom. That is expansion stroke. After completion of the expansion stroke, then all these burned gas should get exhausted. So the last stroke should be exhaust stroke, where the piston moves up to expel all burned gas out of your engine. Okay. So you have to remember that this engine has 4 strokes as one cycle. And now, piston moves up and down, up and down. Okay. So 4 strokes basically are same as the 2 rotation of your crankshaft. So every 2 rotation makes one cycle of this engine. Then the question is, how can we make this spark ignition engine in terms of thermodynamic point of view? How can we do thermodynamic performance analysis of such engine? So in order to do so, Otto, the German engineer, invented basically that is invented by the Otto, okay, the total cycle. And he called it as the Otto cycle, or by implementing ideal assumptions into the cycle, we call that as the ideal Otto cycle. In the ideal Otto cycle, we ignore intake stroke and exhaust stroke by assuming that the pressure inside during the strokes are same as the atmospheric pressure. Instead, we take care about the compression and expansion, and in between, combustion process is considered as the heat input process, and exhaust process is converted to be the heat rejection process. Now, let's take a look at this diagram about the ideal Otto cycle. Okay. Now, this ideal Otto cycle has 4 processes. The first process is the ideal or isentropic compression process, where the piston goes up to compress the air, which is the working fluid of this cycle. Okay. Then we have heat addition process, but because combustion happens so quickly as a result of spark ignition from the spark plug in a real spark ignition engine, we can assume that this heat addition process is basically constant volume heat addition process. So that is the second process that we have to consider. The third process is then the expansion process, which is also ideal. So this expansion process should be isentropic expansion process. And the last process is heat rejection process, which models the exhaust blow-down process in real engine. So as soon as we open the exhaust valve, because of high pressure inside the cylinder, expels most of exhaust gas instantaneously. So this blow-down process can be modeled as constant volume heat rejection process. Again, you have to remember that working fluid is totally the air. Okay, we don't worry about fuel anymore in the ideal Otto cycle analysis, and also we assume that this air can be considered to have the specific constant specific heat. Then we use the cold air standard assumption. If we still consider the variable specific heat for the air, which is an ideal gas, then we basically can say that we use just a standard air standard cycle analysis. Then, can you really draw the PV diagram and TS diagram of the ideal Otto cycle? So we went through this PV diagram sketch and TS diagram sketch, and please take a look at this slide one more time, because as I said before, that is really, really important to be able to draw the PV diagram and TS diagram for all cycles we are going to talk about, including the Otto cycle. So please make a pause and take a look at those PV and TS diagram, and please check if you are able to draw these diagrams by yourself.